Yes, thank you. Thank you very much for the presentation, introduction. Yes, as Ray just said, my name is Martin. I'm here to talk about what we're doing in GaAsP Solar, what we're developing, and what Ray just told you, and the title sort of give away some of it, but I'll show you more in this presentation. Now, first of all, I'd like to present those we have been working with, because we're not alone in this development. We have strong collaboration with University College London. Professor Huiyan Liu from the Semiconductor Physics Group. He is the MBE grower. He is responsible for the MBE system, and this is where we do our nanowire growths. And then we're working closely together with Peter Kostrup. He was a PhD student originally on the project that we used to produce most of the results that I will show you today. Right now he's finished his PhD last year, and he's probably associated professor by next year. He's really, really good. Sponsors the project for the PhD project was the Danish National Advanced Technology Foundation. Really nice guys, nice money. And then I should perhaps also include the, I haven't written them here, the investors in both Sunflake and GaAsP Solar. That's the venture capital firm, Seed Capital Denmark. And finally, the predecessor of GaAsP Solar, Sunflake. We had Henrik and Jeppe working there. They've done a lot of the work that I'll be presenting now. So these people are really helping a lot in, let's see if I can, in the work that I'll be showing you here. Okay, now start out by the motivation, the background of what we're doing. You all know this, probably all seen this before many times, so I'm not going to scale it up. As you know, if you look at this function of time, you have the efficiency, and here, at the bottom right, you have the polymer organic solar cells, plastic solar cells, and then as you go up, you have the thin films, and you have the multicrystalline silicon, the monocrystalline silicon, and then you end up with the 3,5, the monocrystalline 3,5 single junction gallium arsenide, and then multi-junction, triple junction gallium arsenide, phosphide, indium phosphide cells. You could also plot the cost as function on the Y scale here, and then you will have the cheap, inefficient plastic solar cells, zero cost, and the cost will then increase as you go up until you get to the silicon and the 3,5, and if you look at the dollar per watt peak, these are just some rough production numbers. Then, as we just learned, the cost for making a crystalline, monocrystalline solar cell production scale is close to nothing. It's below $1 per watt peak. You don't earn any money on it, no. And the typical production efficiency, well, for sun power is slightly above 20%, for the Chinese cells is slightly below. But this is what you have. You have triple junction cells. The highest record efficiency, one sun efficiency here is, I believe, right now is 37%. Above double that of the silicon solar cell. Now, the problem is that the cost, if you buy in large volumes, you can probably purchase 1 square centimeter of these triple junction cells for around $5 to $10. So imagine if you want to have the iPad covered with triple junction solar cells, it's going to be really expensive. And the huge gap in cost between the monocrystalline silicon and the multi-junction 3,5 sort of leaves space for a market here, because we know that the market demands solar cells which have a high efficiency but a lower cost, because right now for products like portable consumer electronics and CPV and auxiliary power supplies, these cells are either too inefficient or too expensive, or they're too sensitive to the spectral distribution of the lighting in the room. So even if you purchase a lot of these 3,5 multi-junction solar cells and covered your iPad with them, the efficiency in this room wouldn't be very much, because the different junctions will not be current matched. So you need to have a high efficiency cell at a lower cost. And probably already figured it out. You have to use the 3,5 materials in small volumes to get the high efficiency, and you have to get rid of the high cost germanium substrate that these are grown on, and use silicon instead. So you need basically to grow to grow 3,5 directly on a silicon substrate. Now, there's been many theoretical investigations of what efficiency can you expect if you have a bottom cell of 1.1 electron volt of the silicon and top cell of around 1.7, 1.8 EV. And this calculations from 2006 say you get around 39% efficiency. Other simulations say 42, others say 37. We don't know, but it's in that range. So basically a 3.5 on silicon tandem solar cell will give you an efficiency that is close to that of the triple junction cells, but at a cost that are substantially lower. You get rid of the germanium substrate, replace it with silicon, and you use hopefully less 3.5 material. Now, this is not new. I mean, people have known this for more than 3 decades, and they've been working on it for more than 3 decades. But the huge problem here is that if you want to grow 3.5 directly in silicon, well, first of all, there's a 4% difference in the lattice size. And the average distance between the atoms in the silicon crystal and the 3.5 crystal is at least 4% higher, depending on what 3.5 material systems you have. And just as important, if you heat up your solar cell, then the thermal expansion coefficient of the 3.5 material is at least twice that as the silicon. So imagine you have a tandem 3.5 on silicon solar cell in the desert, and at night it's 0 degrees, and during the day it's 70 degrees in the CPV system. Then this heating and cooling will induce a lot of strain in the crystal. And the strain from the lattice mismatch and from the thermal expansion coefficients, the difference in that, is going to introduce a lot of defects. So the efficiencies that we have observed on these 3.5 on silicon tandem cells is substantially lower. And just a quick overview of what we've seen, then perhaps I'll just start out by showing this image from 2005 from NREL, and they do it a lot better right now, I should say, but this is very illustrative of what is the problem. Here they've grown on a silicon substrate, and you see the beautiful crystallinity of the silicon, and then they've grown a lattice match gallium nitride phosphide layer, thin layer on top of the silicon. And then they've started growing gallium phosphide, and then they graded it up to gallium arsenide phosphide, and then they've grown the solar cell on top here. Now, there's a whole lot of defects due to the strain induced in the crystal. They grew this structure at, I guess, around 650 degrees, and immediately after growth, they cooled it to room temperature. So already there, they have the extra thermal strain induced, and then it looks like not very nice, a lot of defects. And the efficiency you got was 5.2% for a dual junction cell. And I mean, you can imagine if you're low energy photon coming in and you're not absorbing this part here, and then you should be absorbing the silicon substrate, but you have to pass through more than 2 microns of defect-filled material, and it's going to destroy the conversion efficiency of the cell. Now, another type of material is gallium arsenide phosphide, 1.7 EV band gap, has the record efficiency for this composition here of 9.8% for a single junction cell. That is just the top junction. When they grew it on a silicon solar cell instead, the efficiency actually dropped, again due to defects. Now, when people are working on this, they're trying to get around this by perhaps growing on virtual substrates. So they, instead of having a silicon solar cell, they also have a silicon substrate, then grow silicon germanium on top of this, so they have better lattice matching. And then they grow 3.5 materials on top of that. And they got some really huge, really high efficiencies. And I think next month, actually, the group led by Professor Alan Barnett at the University of New South Wales in Sydney, they're going to present results of an efficiency of around 20.8% at the 39th IEEE conference in Florida. So they're improving the efficiencies a lot, but it's not the true low-cost substrate anymore. It costs extra to grow if it's actually germanium layer on top of a silicon solar cell. So it's not as low cost as it could be. The highest efficiency I've been able to find was this aluminium gallium arsenide on silicon, grown at the Nagoya Institute of Technology. They published this in 2005. Problem was that then, even though they got this high efficiency, they could never really improve on it. They never got further due to the intrinsic properties of the material composition. I mean, the strain, they couldn't get rid of it. So they stopped working on this cell after a few years. So it won't get any higher than this. They stopped working on it. So 3.5 on silicon, it's been known for more than 3 decades that it will be a nice solution for a high efficiency, low cost solar cell. Now, they haven't been able to grow. We believe, and unfortunately also other research groups and universities believe, that the solution to getting around this lattice-matched-induced strain and the thermal-induced strain is the use of 3.5 nanowires. Now, for those of you who don't know what a nanowire is, there's a quick introduction here, in case you haven't heard about it before. Essentially, 3.5 nanowires, the indium, gallium, aluminium, arsenide, phosphide, and timonite nanowires, composition of these. They're grown in the 111 crystal orientation, that is 35 degrees angle relative to the 000 orientation. 011, 100 normal crystal orientation you have. So that's why these have an angle. If you use a crystal-oriented substrate that is 111, then these will grow perpendicular to the substrate surface. These nanowires are microns long, nanometers thin, and it's difficult to see in this image, but they actually all end with a gold catalyst particle. Now, this is non-lattice mesh growth. These are indium arsenide nanowires, and they're grown on a gallium arsenide substrate. There's 6% difference in lattice matching. It's possible with nanowires because they have such a small diameter. Now, the diameter of nanowires is controlled by the growth catalyst, and they have the hexagonal shape, if you see here directly from above. Now, the way we grow these nanowires, or these are grown, is basically you take your gallium arsenide substrate, you load it into your growth system, in this case it's molecular beam epitaxy, then you heat the substrate, and because it's gallium arsenide, you have to have a group 5 flux on of arsenide atoms. And when the substrate is heated, we deposit a thin layer of gold on the surface, and this gold will then form small gold droplets. It will interact with the substrate and form a gold gallium eutectic alloy. And when you then want to start to grow your nanowire, you just open up for the gallium atoms in the MBE system, and it will impinge on the substrate surface, diffuse around, and at some point it will meet the gold catalyst particle, becomes incorporated into it, and it will supersaturate this gold gallium alloy, and will sort of start pushing out gold underneath it. Not gold, the gallium underneath it. And because you have a group 5 flux on, then it will come out as in this case, gallium arsenide. So you will be growing a gallium arsenide crystal beneath the gold catalyst particle, and then it just, as long as you continue the flux of gallium atoms, you can just grow the wire higher and higher. This growth method was published first time in 1964 by Wagner and Ellis. They grew silicon wires, not as much nano at that time. And they could see that at the temperature they were growing, then the composition, the gold silicon alloy would be liquid. So therefore they named this growth method the vapor liquid solid VLS growth mechanism, where the vapor coming in, the liquid droplet, and the solid nanowire crystal. So it's a well-known growth method. Now you control the height of the nanowire, as I said, as a function of growth time, diameter, controlled by the catalyst. Also, the position of the nanowire is controlled by the catalyst. So instead of depositing the gold in situ on the substrate surface, if you then deposit each of these gold catalyst particles prior to loading the substrate, you can actually grow beautifully positioned arrays of nanowires. The morphology is controlled by temperature, flux radio, growth rate. But the most important part for this use we have for it is, as I said, it can be grown on non-lattice mesh substrates. And the reason is that this is, as you can see, a TM image of a gallium arsenide nanowire with a gold gallium solid droplet on top. It's been cooled now to room temperature. And you can see that this is a Wurtzite, cubic Wurtzite structure. You have the AB orientation. And you also, if you look closer at this image, you will also be able to see that it's grown in a 111B direction. That is, each of these monolayers terminating, each layer is a group 5 atom. It's arsenide, and you have the gallium atom below. Now, imagine that we had grown this on a silicon substrate, that this is a silicon. Then there will be a 6% lattice difference between the gallium arsenide and the silicon. That means that the lower array of atoms here, the lower columns of atoms, will have to be sort of squeezed together by 6%. And it can do that. There's a finite number of atoms here, so you can squeeze it. It can tolerate this. The next monolayer you grow will then be slightly less strained, and the third one will probably not be strained at all. So therefore you essentially have a strain-free growth of the nanowire. All strain is located at the interface, And because the interface is so narrow, it can absorb the strain without defects. And the same goes for thermal induced strain. You have had arrays of these nanowires being cooled in liquid nitrogen and heated again, and it still maintained their properties. It can absorb the strain. So if you want to grow 3.5 directly in silicon, the solution is 3.5 nanowires. We believe, at least. Now, these are grown with gold, and there's a small problem with gold. If you want to grow on a silicon solar cell, it's not always a good idea to start out putting gold on a surface and then heat it to 650 degrees for an hour, because the gold will diffuse into the silicon and create a lot of defects, and that will minimize the efficiency of the solar cell. And also, you know that when you grow the gallium arsenide nanowires, you might not have seen it before, but you can actually pick out individual gold atoms that are included in the nanowire crystal during the growth, and you don't want to have gold inside your nanowire crystals. And finally, a more practical problem. Not very many growth systems will allow you to introduce gold into it. It pollutes the growth system. So unless you're a nanowire grower, you basically never ever want to have gold into the system. So it minimizes the amount of growth systems available for your work. So get rid of gold, very important. Fortunately, the group led by Professor Anna von Goberti-Mural, she's now at the EPFL in Lausanne, she spearheaded the development of a new growth method called self-assisted growth. And here you replace the gold catalyst with, in this case for gallium arsenide nanowire, you replace it with a droplet of gallium. Now what they figured out was that they could take a gallium arsenide substrate and then deposit a nanometer thin layer of silicon dioxide on the surface of this substrate. When you then start to grow gallium arsenide, just atoms impinging on the surface, the group 5 material, the group 5 atoms will re-evaporate immediately, whereas the gallium atoms will diffuse around on the oxide surface. It will form small gallium droplets, and then the group 5 material impinging on these gallium droplets will be absorbed and supersaturate the gallium droplet. And at some point, the gallium droplet will find a small pinhole in the oxide layer and get into contact with the crystal underneath. And when it does that, it can start to nucleate gallium arsenide. Now, if you're very good at controlling your growth conditions, ensuring that the amount of gallium atoms being nucleated as gallium arsenide is the same as the amount of gallium atoms entering the droplet from the group 3 flux you have in the growth system, then you can actually maintain the gallium droplet on top of the nanowire throughout the growth. So all of a sudden you have gallium-assisted growth, gold-free growth of gallium arsenide nanowires. Now, it didn't take long for people to realize that since we can grow these nanowires on non-lattice mesh substrates, then replace the gallium arsenide, very expensive gallium arsenide substrate with a silicon substrate. I mean, that's easy. And a good thing about the silicon substrate is that when you take it directly from the box, it comes with a native layer of silicon dioxide on top. So you can actually now just, and we've done this many times, you order the batch of pack up of silicon substrates, you just take it directly from the box, load it into the growth system, and you can grow these gallium-assisted nanowires without any problems, more or less. Now, what you can also do is to put on a thicker layer of silicon dioxide. So this is a p-doped silicon 111 substrate, p-type, and here we have 30 nanometer of silicon dioxide on top. And what we've then done is we etched holes in this layer of silicon dioxide. So removed the oxide layer specific areas. It's around 100, 150 nanometers in diameter. So when we start growing, the only possibility for the gallium droplet to get into contact with the substrate surface is in these holes. So we can grow positioned gallium arsenide nanowires. This is seen from an angle of 25 degrees relative to the normal on the substrate surface. And these nanowires are roughly 2 microns tall, and they are all terminated with a gallium droplet. And you can see that the droplet, the tapering of the nanowires, sort of inverse tapered. The gallium droplet simply becomes larger during growth, so we haven't controlled the fluxes well enough here. We have too high a gallium flux during the growth. These are grown at a growth rate of roughly 1 micron per hour for 20 minutes. So we grow 2 microns tall nanowires using what bulk would have been around 350 nanometers of growth material. Now, once you have done this, the next thing that comes into mind is, of course, let's make a solar cell, right? Because you already have a p-type substrate here. So if you dope the core nanowire p-type, then you will have an epitaxial relation between the p-type core nanowire and the substrate. So you can contact the core through the substrate. All you have to do is to get rid of the catalyst particle here, and that's fortunately very easy to do. Obviously, to the gold catalyst, then you can get rid of the catalyst particle simply by closing the group 3 flux, closing the flux of gallium atoms during the growth. So within a few minutes, all the gallium in the droplet will be absorbed and turned into gallium arsenide. And then when you start growing again with the gallium flux on, you will be growing on the side facets of the nanowires. You will no longer be doing the catalytic vapor liquid solid growth mechanism of the nanowire. You'll just be growing vapor solid on the side facets of the nanowire. So if you just sketch this, you have your substrate that are positioned and patterned. Then you grow a p-type substrate and you grow a p-type core nanowire, get rid of the gallium catalyst, grow the intrinsic shell around it, grow an n-type shell around it, and then you have your core shell, PIN, solar cell. And now you contact the inner core through the substrate, so when you want to contact the outer shell, you should just have an insulating layer on the substrate surface, expose the top, and then put down your contact material, and you have your solar cell. Now this is the sketch of it, and in real life it looks like this. You have the growth substrate with some alignment marks on here, so we can find we just grew 1 nanowire. Well, actually we grew many, but we contacted them individually. And have the position grown nanowire here, filler and S-back, just the top exposed, and put down the transparent top contact, in this case IGO, and then you're ready to measure. So we have your system, we use SU8 as the filler in this case. Now, big surprise, lousy efficiency, lousy open circuit voltage, right? 0.43 volt. The fill factor is not very good. But the short circuit current, I mean, if you just look at the raw data, then you have a current density of 180 milliamps per square centimeter. And that's a lot. It's huge. And the reason, of course, is that when you have a 2 or 3 micrometer tall nanowire standing directly on the substrate surface and the light is impinging from above, the collection area of this nanowire is larger than the cross-section area. It collects photon from around it also, sucks in photon. So if you just look at the efficiency as calculated as function of the cross-sectional area of the nanowire, then you have 40% efficiency, huge. But if you include these data and this, we grew this nanowire, it was grown by Peter Kostrup, and we did the pre and post growth processing, one-time characterization, all this, and then we shipped it to the Collaborators group in Lausanne. And they did some characterization as function of position, absorption as function of position. So they took a laser, a line laser, and just scanned it across the nanowire. And as function of position, they can see how much current it generated, so how large an area did it absorb from. And the result was that it could absorb from a cross-sectional area 8 times its cross-sectional area. So basically, it concentrated the light, has built-in concentration ratio of 8, this nanowire. And if you take that into account, then the macroscopic cell with this type of nanowire will have an efficiency of only 4.6%. Now, these data was published in February this year. And yeah, both University of Copenhagen and EPFL sent out press releases at the same time, so you can imagine this headline, beyond the Shockley equation limits, pushing the limit for theoretical maximum efficiency. It attracted a lot of noise. The bottom line here is that nanowires, they're not only good for getting rid of strain during growth and during thermal changes, actually it has a built-in concentration ratio. So the open circuit voltage of your nanowire is going to be improved by this built-in concentration. Just a few percentages, not much. But the theoretical peak efficiency you can get will be slightly higher than for a bulk system. It will take some years before we will be able to show this, many years. But in theory, you can go beyond the efficiency of bulk gallium arsenide single junction cell when you use nanowires. Now, this is all 1.4 electron volt band gap, and we needed 1.7, 1.8 in order to get the high efficiency. So if you look at the map of the world for 3.5 MBE growers, that includes silicon and germanium, you can see if you want to go above 1.7, then there's only a limited range of possibilities available to you. And if you look closer at this, then you will quickly figure out that the gallium arsenide phosphide material systems is where you want to go. Now, when you grow the nanowire gallium arsenide phosphide, you need to be able to control the composition of the phosphide, of the group 5 atoms very accurately, because if you change this slightly, you will change the band gap of the material and you will change the lattice constant. So you need to control the composition of both the group P, the phosphorus and the arsenide atoms during the growth, and later on when you grow the shell around it, you also need to be able to control the composition in the group 5 materials, because the shell has to be lattice matched to the core nanowire. Then, of course, you need to be able to grow defect-free crystals and dope them N and P type without affecting the crystallinity of the nanowires. Now, we did this. I should say from now on, all the growth that I'll be showing will not be precision growth. It will be this growth where you have the random precision. You just take the silicon substrate straight from the box and then grow on it. And the reason is that though the uniformity of the properties of the nanowires are significantly worse, then it's a much faster growth method. You can do 3 growth a day, whereas if you do the precision growth at like once a week. So now it's randomly positioned nanowires, and that means that the density of the wires are also much higher. We have a couple of nanowires per square micron. These gallium arsenide phosphide nanowires, band gap 1.7 electron volt, all terminated with a gallium droplet on top, all having perfect, almost perfect crystalline zinc blend, hexagonal zinc blend crystal structure. What you see here is known as a twin defect, and it's essentially you grow a zinc blend structure, and then at one point you suddenly rotate the crystal 60 degrees, so essentially you get one monolayer of wurtzite instead of zinc blend. Doesn't really matter. Essentially it's defect free. The amount of phosphorus atoms in the group 5 atoms is roughly 20%, roughly. At the beginning of the growth, we changed the growth condition slightly, so therefore we expected a low composition of the phosphorus. To get 20% of phosphorus inside the nanowire, we only had to use 15% phosphorus atoms in the group 5 flux, so 85% arsenide, 15% phosphorus. 503 ratio of 50, and the growth rate, in this case we only used roughly 300 nanometer per hour growth, and we grew for half an hour, so these nanowires are grown, which what for a bulk growth would have been roughly 150 nanometer thin layer of 3.5 material. Just a quick go through of the entire nanowire structure. Zoom in. At the bottom part here, it's difficult to see, but at the very bottom and the very top part, you have some multiple twinnings. These are not because of strain-induced. It's not strain-induced defects. It's because the growth parameters at the top and the bottom of the nanowire are not optimal. The collection areas for the gallium atoms is different in the start and ending of the growth than it is during the nanowire growth. But for the rest of the wire where light will be absorbed, you have essentially perfect single crystal zinc blend nanowire structure. Now, when you want to grow the shell around this, you should make sure that the shell is lattice matched. And the problem is that the incorporation efficiency of the group of the phosphorus atoms in the nanowire during the core nanowire growth is significantly different than it is during the shell growth. Because when it becomes incorporated with the gallium droplet, the phosphorus atoms, then you have a very high incorporation ratio. So we use only 12% phosphorus in the group 5 flux during the core nanowire growth. But when we wanted to do the shells, we needed a lot more, so initially we started out with 55% phosphorus in the group 5 flux. And these are X-ray diffraction data. basically you can see a peak from the silicon crystal lattice size, and then the black curve here, you see two other peaks. One is from the core nanowire growth, and one is from the shell around it. So this is completely non-lattice mesh core shell growth. Then we simply just modify the amount of phosphorus, and slightly better, almost just one peak. Better again than the final growth here. We have 30% of phosphorus atoms in the group 5 flux, and you get a perfect lattice mesh core shell growth. This is an image of one of the core shell nanowires. It's really huge, this one. The one we're measuring on is not as thick. But what I want to show you with this one is the tapering. This is due to, as I said, they have a very close proximity. When you grow them, they're very dense on the substrate. So you have the nanowires standing next to each other, and the flux is coming in at an angle. So therefore, you will be growing your shell mostly at the top of the nanowire. This is because we use non-precision growth. For precision growth, you will get rid of the defect. But it has a nice effect then that we know that we have mainly P-type core down here, and we have N-type shell up here. So when we want to contact it, what we're doing is basically we harvest all the nanowires. We take a piece of the growth substrate, and then just put it into isopropanol and give it some ultrasound. So you break off all these nanowires and just float around in the IPA, and then you take a droplet of this IPA and you just deposit it on the substrate where you want to have your individual nanowires. And this is an optical image of such. And when you have the real high quality optical image, you can see not just individual nanowires lying around, but you can also see the tapering of nanowires. So you know which end is N and where P is, and then you can just define your contact pads using E-beam lithography. And you start out by making the P-type omics, because define the contact area for the P-type omics, and then just before you put down the P-type contact material, you etch the nanowire slightly so you get rid of any N-type shell that must be, to only contact the P-type core of the nanowire. And afterwards you do exactly the same steps for the N-type contact materials. So there you have your single nanowire solar cell NP in a core shell geometry. And here I should say that the thickness of this nanowire is at max up here is 400 nanometers. And now it's not standing perpendicular on the substrate anymore, so it's no longer absorbing a lot of the photons impinging on it. Right now, because of it, it's very thin, so you can expect that half of the photons impinging on it will basically just either be reflected or pass through. Don't know how much, but there are theoretical modeling saying that up to 50% of the photon flux coming in will just either pass through or get reflected. So this geometry is not as good, but it's as the one standing straight on the substrate. But it's very good for just characterizing the individual nanowires from growth to growth to see any improvements you've made. So we measured, of course, on these devices, and the best gallium arsenide phosphide nanowire we got initially was low efficiency, 6.8%. Open circuit voltage, 0.76. So compared to the maximum theoretical possible for 1.7 electron volt band gap, I mean, the VOC is slightly more than half of what we should get. The short circuit current is only also slightly more than 50%, but here we're not as worried because of the geometry of the nanowire solar cell. We're not supposed to absorb as many photons. Fill factor is lousy, ideality factor is not very good. But with nanowires, you have a system that, well, you have a huge surface to volume ratio. Nanowires is all surface and very little volume. So these are unpassivated gallium arsenide phosphide devices. So we did the growth again, but this time we then passivated it with approximately 10 nanometers of N-doped indium gallium phosphide as a surface passivation layer. And now the results improved. The efficiency is now 10.2% of this one device, the best device, I should say. Short circuit current improved a bit, but open circuit voltage improved, fill factor better, and the ideality factor is also improved. So, okay. If we just compare these two, we did a lot of these individual nanowires, and you see the average efficiency of the unpassivated ones is around 6.8%, around 2.9% that is, and the average efficiency of passivated is around 5. So we have an increase in efficiency of around 70% just by adding a kind of passivation layer to the nanowire. These results we published in January. It's not a catchy as headline title as the other article, but for me this is more important. I mean, here we have for the first time shown that you can grow the 1.7 electron volt 3.5 material without the use of gold directly on silicon and actually make solar cells of it. So you have all the individual components that are necessary in order to grow the perfect tandem solar cell. And we know we can even get a higher open circuit voltage than for regular cells, in theory at least. Now, results that we didn't publish here is those on concentrated photovoltaics. So we just also did just increase the amount of photons coming in. See the results for the best device here, the efficiency at 1 sun of 10.2%. And as we increase the amount of suns to 25 times concentration, what we essentially see here is the textbook example of a high series resistance. Now, I should say we are still working on these results here, so we haven't gotten any good conclusion yet, but I'm showing you this anyway. You see, as the number of suns increases, they've just had a higher series resistance. The efficiency goes up slightly, around 11.5%. The short circuit current increases as it should, as a function of concentration. The fill factor decreases, again a sign of a higher series resistance. The open circuit voltage start out just increasing slightly and then it saturates. So all in all, it's not ideal. And we believe that is because to poor contact to the nanowire. And we've been using the annealed p-type omics, but in this case we used an n-type omics that consists of 40 nanometer germanium, 60 nanometer gold, and then some diffusion barrier and more gold on top. And in this case, we didn't anneal the omic contact. And we didn't do so because we know, I mean, this is an n-type contact material that's been known for 20 years. And when you start to anneal this, it will diffuse up to, for instance, 100 nanometers into the 3.5 material. And when you have some layer thicknesses in your core shell nanowire that are significantly thinner than 100 nanometers, you don't want to diffuse material through all these layers. So therefore, this is a non-annealed contact. And it really affects the performance of the solar cell at higher suns. Now, we then did some more processing, and we took nanowires from the same growth, but we contacted it differently with n-type omics. This time we used 100 nanometer germanium, 100 nanometer gold, and then we annealed it just slightly. Usually you anneal at above 400 degrees Celsius. We just used 300 degrees in just 4 minutes, just slightly. We wanted to see if we could improve the contact resistance. And what we got here, the setup we have, we can't go beyond 25 suns in concentration. And you see the IV curves here. It's beautiful. There's no sign of any series resistance all the way up to 25 suns. The efficiency, this is one of the devices which start out with an average efficiency of 5.5%, increases to 11.5% from 1 sun to 25 suns. Short circuit current scales linearly with intensity as it's supposed to. The fill factor also increases with intensity as it's supposed to. The open circuit voltage also increases with intensity, but not as it's supposed to, because we were expecting to see an increase in open circuit voltage of around 85 millivolts from 1 sun to 25 suns. What we saw was 300 millivolts, a huge increase in open circuit voltage. Now, you could then start saying that, well, this is because I have a built-in concentration and all this, and we don't think it's not the case. We're still working on this, but essentially, we believe that the reason to these results with a huge increase in open circuit voltage is that we still have a kind of faulty design. I mean, let's face it, we're a company, we wanted to produce this gallium arsenide phosphide solar cell as quickly as possible. So we did so with just from the very first nanowire growth to this one, we spent a total of 30 nanowire growth on this. And we didn't stop in between and sort of optimize things. The only optimization here is the surface perturbation layer, and that just added one time. So we haven't optimized the doping densities, we haven't optimized the doping levels, the layer thicknesses of the different layers in the core shell geometry, and we haven't optimized the surface perturbation layer. So there's still a lot of work to be done. And we believe that what we see here is that at one sun, this nanowire is sort of being affected. We see the effect of all these defects, the faulty design, the non-optimized design of the nanowire is showing off in a very low open circuit voltage. But this is then compensated as we go to larger concentration levels. So what we see here is dominated mainly by what it would be like this solar cell if we had optimized some of these things, the doping densities and layer thicknesses and all this. So we interpret these results that there's still a lot of improvements to be made in these nanowire solar cells. But we haven't been working on for very long. So we're positive, we're optimistic. Now, just brings me to the summary of this. As I said, the market demand the high efficiency, lower cost or medium cost solar cell. And we know that this can be done with 3.5 on silicon. And gallium-assisted nanowire growth is compatible with the current silicon solar cell technology. You can put these two together. And we can grow the correct band gap, 1.7 electron volt, directly on this silicon. And even though we have some not very good contacts, then if you remember the record for gallium arsenide phosphide solar cells grown directly on silicon bulk, and that was 9.8%. So well, we are already at sort of record level efficiencies for this system, and we have not been working on it for 3 decades. So it's very promising. So the next step that we will be doing right now is to combine each of these individual parts, that is, grow the gallium arsenide phosphide nanowires positioned on a silicon solar cell and then optimize the contacts. Because contacting these nanowires right now looks as being the biggest hurdle of them all. I should just finish by adding that there's a paper that came out a couple of years back where actually Professor Lapierre here, he calculated, modeled that for a gallium arsenide phosphide nanowire tandem solar cell, gallium arsenide phosphide nanowire standing on a silicon solar cell, he expects an efficiency of 33.8%. I don't think you included the added open circuit voltage from the built-in concentration, so it could be better. Now, in that modeling, if I remember correctly, then you assume that the silicon solar cell will give roughly 11 percentage points to this efficiency. So if you just take the results we have now and say, okay, we can grow, let's say, a 10% efficient 3.5 cell on top, and then add, certainly you can make a silicon solar cell, right? So then add the 11 percentage points from the silicon substrate, you will already, with these results, be above 20% efficiency. So we think this is looking very promising, and well, the problem is, of course, how long will it take to put these together, but hopefully we will have sort of a prototype within the next year, and then we'll see what efficiency that will have. So with that, I would like to thank you for your attention, and thank you.